So now it has 9 positive charges and 9 negative charges. Now it's balanced. So it's not positive, it is neutral, and it becomes a neutron. And that is where the other proton went. Electron capture. Let's do electron capture. So here is beryllium 7, and it's going to capture an electron. So the electron weighs nothing. There's the electron. So beryllium is still going to weigh 7, but it's not going to be beryllium anymore, right? It's actually going to be lithium now, because its number of protons went down to 3. How did that happen? Because here you have kind of a similar thing. You had a proton. Let's say you had like 10 positives and 9 negatives. So it's positively charged because the positives outweigh the negatives. Then all of a sudden comes flying in an electron. The electron gets added here, and now you have 10 negatives, 10 positives. So now the proton's balance, it's neutral. The proton then becomes a neutron, and that's where this proton went. It just turned into a neutron. So you only have 3 protons in the nucleus, and now the element is lithium. All right, last page of the notes. Let's go forward here. All right, this stuff on half-life, this is not on your test, not on a test. It will be on a quiz, will be on the final, all right, but it's not on the test. So what is half-life? It's the time required, all right, for half of a sample of radioactive material to decay. That's what it is. So stepwise count on the half-life. You could do this really simply. You could just divide by 2 a bunch of times. So for instance, I'll show you 2 different ways here. If you have iodine 131 looks like this, iodine 131, and the atomic number of iodine is 53. There you go. And if the half-life is 8 days, what fraction of the original sample would remain at the end of 32 days? Well, 8 goes into 32 4 times. That's 4 half-lives. So what you do is you say, okay, well, after 8 days, you would have a 1/2, right? And then after another 8 days, you would have 1/4. And then after another 8 days, right? This is our 3rd half-life, you would have 1/8. And then after another 8 days, you would have 1/16. And that's how much you would have left over, because you had 1, 2, 3, 4 half-lives. You would have a 16th left of what you started with. And if you divide 1 by 16, you get 6.25%. So if you had 100 grams, right, then after 4 half-lives, you'd have 6.25 grams. And I'll show you, you can calculate this with a formula. Here's the formula. It goes like this. Let's just say you had 100 grams of the iodine 131, right? And what you're going to do is you multiply it times 1/2, and then you're going to raise it to the power of the number of half-lives. How many half-lives did we have? We had 1, 2, 3, 4. So raise it to the power of 4. Do that math. 100 grams times 1/2 raised to the power of 4. That gives you 6.25 grams. And 6.25 grams is equal to 1/16. 1 divided by 16 is 6.25%. All right, let's take a look at this one over here. This is a graph. Remember, this will be on the quiz. It will be on the final, not on the test. What is the half-life of this substance? Let me erase some of this so you can see better. What's the half-life of this substance here? Well, I'm going to hopefully zoom in so you can see. It's kind of grainy. Not so good. All right, well, let me just tell you what it says. Excuse me. Here it says 80. All right, that's 80 up there. This is 40. This is 20. There's 10. Okay, so, and this is 2, 4, 6, 8. So we start with 80. Let's say we have 80 grams. When do we get 40 grams? Oh, sorry, 70, 60, 50, 40. This is 40. Sorry, I couldn't even read it. That was 60. So half of 80 is 40, right? So you come over here, you're like, where's 40? It's there. All right, half of 40 is 20. Where's that? It's there. Half of 20 is 10. It's there. Notice something? Half of 80 is 40. How long did that take? It took us 2 days. Half of 40 is 20. It's right there. How long did that take us? 2 days. All right? And then half of 20 is 10, and that took us 2 days. Okay, so every 2 days we're losing half of our sample, so the half-life is 2 days. Okay? Oh, sorry, I put that in the wrong spot. So the answer is 2 days. Okay, so you can do the calculation. T half amount of time that has passed over n. That's a different way to do it. Where T half is half-life time. Right, so the time for one half-life. Or you can do this calculation, which I showed you up top, which is half raised to the power of n equals what, and then mf is what you're going to have left over, and m1 is what you started with. It's initial and that's final. So the mass initial times half raised to a power equals the mass final. All right, so these are both going to give you, both of these formulas are essentially the same thing. All right, so let's see here. N is the number of half-lives that you passed. All right. And, sorry, let me just reiterate this. N is this. N is, it's your, no, it's right here. It's your number of half-lives passed, okay? And then the amount of time that has passed, and then that's going to be equal to your half-life time. All right, and then let's go down here. Let's do a couple examples. If you have 20 grams of Pa-224, and it has a half-life of 1 second, how much is left after 4 seconds? Well, pretty easy, right? 4 divided by 1 equals 4. So 4 half-lives. So you do 20 grams, so I'll just do 20 grams times 1/2 raised to the 4th, 4 half-lives. And you'll see that that will equal 1.25 grams. You could have done that the other way too. You could have done 20 divided by 2, and then that answer would be 10 divided by 2, which would be 5, divided by 2, which would be 2.5, right, divided by 2, which would be 1.25. So there's your 1, 2, 3, 4 half-lives, and you get the same answer. Do a couple more examples, and I think that's the end of your notes. Let's just change colors here. If you have 20 grams, right, of Pa-234, and the isotope has a half-life of 7 hours, notice this is a different isotope. This is P234, and that was Pa-224. How long do you have to wait until you only have 5 grams? All right, well, you got 20 grams times 1/2 raised to the x equals 5. And you can solve for x if you got your fancy calculator, or you can do it the old-fashioned way, right? You can say 20 divided by 2 is 10, divided by 2 is 5, and you say, wait a minute, that's 2 half-lives, and, excuse me, and 2 half-lives times 7 is 14 hours. My units there, because it's 7 hours per half-life, and that's your answer, 14 hours. Let me pause it for 1 sec. One here, the half-life of chromium-51 is 28 days. Sample contained 510 grams. So how much would remain after 56 days? So 56, right, divided by 28 equals 2. So that's 2 half-lives, right? So 2 half-lives, and therefore this will be raised to the power of 2. And that's going to give you an answer of 127.5 grams left over at the end. All right, I think that's the end. Okay, so we have one more page. So on the back side of this page, I'll just fill in these notes so we'll finish it all up for you. Alright, so let's just take a look. How much would remain after 364 days? Alright, so N is going to equal 364 days, and a half-life equals 28 days, right? 28 days for one half-life. So that's going to be 13, oops, dyslexia, 13 half-lives. Alright? And then what you're going to do is you're going to say, okay, well, if I had 510 grams times 1/2 raised to the 13, what is that going to equal? And that is going to equal 0.062 grams at the end. Alright, we'll do, I think there's 2 more half-life problems, and then there's a little bit about fission and fusion. So here you go. 20 grams of radioactive isotope present at 1 p.m. and you have 5 grams remaining at 2 p.m. What is the half-life? So it goes from 20 grams, right? And it turns into 5 grams over the course of 60 minutes. So you know, obviously, that there's 10 grams somewhere in the middle here. And so it should be obvious to you that if we only have 60 minutes, that 30 minutes must have passed here and 30 minutes must have passed there. So 1 hour would have equaled 2 half-lives, and therefore 1 half-life, right, would equal 30 minutes. All right. Okay. Let's go down to number 5, and let's see that the half-life of oxygen-19 is 30 seconds. What fraction of the isotope originally present would be left after 15 seconds? Alright, so there's your half of it's going to disappear after 30 seconds, but you don't have a half-life. You only have half of a half-life, right? So here's what you do. Say you only have 15 seconds, so it's just 15 divided by 30 equals 0.5. So you have 0.5 half-lives. Alright, so let's say you started with 100 grams. If you started with 100 grams times a half raised to the 0.5. When you do that, you're only going to get, I believe it's 7.07 grams. Let's double check that. 100 times 0.5 raised to the 0.5. Yes. Oh, sorry. So, shoot. I'm on the wrong spot. This one should go there. So it would be 70. So 70%, right, would remain, and the fraction would be because it's just 1/2 raised to the 0.5. It's going to be 0.707. That's the decimal, and your fraction therefore is, I guess it wants it in a fraction, but it doesn't have it listed. That's okay. You have your decimal there, and the fraction is just 70.7 over 100. And that's all you need right there. Okay, there's your fraction. Medical applications of radioactivity. You can research this on your own if you want. MRIs and different usage of radioactive material to trace the blood flow in your body, things like that. We won't be tested on that. Fission and fusion. Fission gets used in power plants, right? And fusion that gets used in the sun and in hydrogen bombs. All right. Fusion much more powerful than fission. Fission, you're breaking something apart. You're splitting something that's heavy. You're splitting heavy elements. All right. Into smaller ones. And fusion, you are combining, you're fusing together, you're combining lighter elements